about to show you a beautiful vector-analytic solution to Heron's problem. Now I'm sure that you're familiar with this problem and its classic 2,000-year-old solution. But just in case, let me remind you what they are. You have a straight river and two villages A and B, and you have to leave village A with an empty bucket, go to the river to fill the bucket, and then take the water to village B. And you have to accomplish this task by following the shortest possible path. So the question is, where is that magical point along the river that will produce the shortest path? And that classic 2,000-year-old solution based on geometry is this. What you need to do is find the reflection of point B with respect to the straight line of the river, then connect point A with the reflection of point B by a straight line, and wherever that straight line crosses the river, that's that optimal point that will deliver the shortest path. So let me have this construction drawn in, and then I'll come back and point out why it indeed delivers the optimal path, and we'll also figure out the geometric property that characterizes that special point. Well, here we are, and I think it's pretty clear that APB is the shortest possible path because it is equivalent in length to the straight segment AB1. And any other path, like the one I originally drew, is equivalent in length to this broken line. So it must be longer because in any triangle, the sum of any two sides is longer than the third side. So this proves that this special point P indeed corresponds to the shortest side. And we can also notice that this point is characterized by the fact that these two angles are equal. Well, you can see why that is. It's because this angle equals this one, and this angle equals this one. So geometrically, this point is characterized by the angle of incidence being equal the angle of reflection. What a brilliant solution! What fantastic geometric insight! What ingenuity! Our goal, however, is to construct an analytic framework that removes the need for geometric insight, that removes the need for ingenuity, and instead delivers the same results by applying strict rules of differentiation. That's our goal, and that's what we're about to do for this problem. Okay, let's refer our straight line to parameter alpha, and let's treat this as a typical point on the line. And so we'll call this vector right here capital R sub A, and this vector right here capital R sub B. Okay, and the objective function f, that is the function that we need to minimize, is the length of RA plus the length of RB. And because we're adding the two lengths together, we will not be able to avoid square roots. But that's a good thing because square roots will do a great thing for us in this problem. And of course, we'll express the lengths via the dot product because that's our go-to tool for converting geometric concepts to algebra. So here we go. All right, that's our objective function. So we will now take the derivative of this function with respect to alpha. And because we're looking for the optimal point where this function attains its minimum, we will equate the derivative to 0. Now this is an ordinary function of alpha. It is the square root of something, and yes, what's underneath the square root involves vector quantities. But once we dot them, it just becomes an ordinary scalar quantity. So we can differentiate this function by applying the ordinary chain rule. And what we'll find is 1 over 2 square root of the same thing times the derivative of what's inside the square root. But we know precisely what the derivative of what's inside the square root is, because that's exactly the kind of exercise we just did in the previous video. when we were talking about the derivative of a vector of constant length. Now here the context is different, but the calculation is exactly the same. And we know that we will get 2 times r sub a prime dotted with r sub a. So the 2 2's will cancel each other, and we'll be left with this. And a similar term for r sub b. All right, so now we need to notice that r sub a prime and r sub b prime actually have the same vector value because they both refer to the same derivative, to the same tangent vector of the straight line. Maybe I'll draw it in right here. So both r sub a prime and r sub b prime refer to this vector, which is not necessarily of unit length, because alpha is not necessarily arc length, but they have the same value, which we'll denote by little t of alpha, which we can now factor out of the sum. All right, now let's discuss what we'll see inside the parentheses. What we have here, what we'll have from this term is r sub a divided by the length of r sub a. In other words, we're dividing a vector by its length. So we'll end up with a unit vector that points in the same direction. We'll denote it by little n sub a. A similar thing occurs here. Once this is factored out, we'll have r sub b divided by the length of r sub b. So we'll end up with a unit vector that points in the same direction as r sub b. So we'll call that vector little n sub b. And so what we'll have in these parentheses is the sum of these 2 unit vectors. And so, believe it or not, after just a couple of steps, we have arrived at our final analytical answer. It states that the optimal point is characterized by the algebraic fact that the sum of the 2 unit vectors that point in the direction of these lines is orthogonal to the straight line of the river. So that's all there is to say analytically. But now what we have to do is interpret this result geometrically. And we observe, of course, that the only way that the sum of these 2 vectors can be orthogonal to this line is if these vectors form the same angle with this line. It will only happen when they're arranged like this. In other words, when this angle equals this angle. And we have once again recovered the geometric criterion that the angle of incidence must equal the angle of reflection. So this analytic approach also shows that this point is the optimal point. Except it did not require any ingenuity, any geometric insight, and all we did was follow strict rules of differentiation.